do you mean by pushdown automata? It is an acceptor for every context free language. What is pushdown automata? It is also called as PDA, which is nothing but a finite state machine that has been augmented by a single stack. When we go for defining the pushdown automata is defined as M is equals to K summation tau delta SA. What is K? As you all know, K is a finite set of states, summation is a finite set of input alphabets, tau is a finite set of stack alphabets, the alphabets which are pushed in or popped from the stack. Those are called as tau symbols or stack alphabets. Then S is a state from K, which is an initial state or a start state, and A is a subset of K, which is nothing but the one or more accepting states. Last is the delta is a transition rule. How this rule is written? It is a finite set of, so first one is a state, second is the input symbol which includes epsilon, and third is the string of symbols to be popped from the top of the stack tends to a state. This state may be same state or different state, and the next is again tau star, which represents the string of symbols to be pushed into the top of the stack. So, before starting with designing the pushdown automata, we have to discuss some of the terminologies used here. First one is configuration. What do you mean by configuration? A configuration of a PDA M is an element of K summation star tau star, where K is the current state, summation star is the input that is still left to be read, and tau star is the contents of its stack. And when we talk about the initial configuration of a PDA on input W is S representing the start state, summation star that is string W, and tau star is epsilon. Now say suppose I push first A into the stack, then B, then C, then we will write or read it as CBA. Now after pushing A, B and C, now if I want to insert string S1, S2, S3 so on up to Sn to be pushed into the stack, then the values after pushing is been read as S1, S2, S3 so on up to Sn, then C, B and A. So this is the string return which is pushed into the stack. As we derive a string in the context free grammar, similarly here we obtain the yield for each of the grammar or the rules which are string which has been derived from the pushdown automata, and that is called as yield in one step, written as the symbol used in this form, which relates configuration 1 to configuration 2 if and only if M can move from configuration 1 to configuration 2 in one single step. Let C be an element of either summation or epsilon, gamma 1, gamma 2 or gamma be an element of tau star, that is stack symbol, and let W be an element of summation star. Then if I have a rule Q1 C gamma 1 tends to Q2 gamma in the delta, then the rule Q1 C W gamma 1 gamma derives or yields, if you see here Q1 current state is Q1, current input symbol is C, topmost element of the stack is gamma, Q1 C gamma, Q1 C gamma. Then what to do? Move from state Q1 to Q2. So move from the state Q1 to Q2, consume C. So once the C has been consumed, then the left unread input left is W. Then pop gamma 1 from the stack and push gamma 2 into the stack. So this is one yield. The relation yield is written is reflexive and transitive closure to a single yield. So C1 yields configuration to C2 can also be written as if and only if C1 for multiple yields generates C2. Next, Computation. What do you mean by computation? A computation by M is a finite sequence of configurations C1, C2, C3 so on up to Cn for n greater than or equal to 0, such that C0 is the initial configuration, Cn is a form q epsilon gamma for q belonging to some state and gamma belonging to some string in the stack symbols. Then C0 derives C1, C1 derives or also called as yields C2, C2 yields so on up to Cn. Next terminology, what do you mean by non-determinism? If M is in some configuration Q1 S gamma, it is possible that for this one configuration, the delta can contain exactly one transition that matches, only one transition for this configuration. At that time, in that case what happens? M makes one specific move, which is a specified move. Other alternative, if the delta contains more than one transitions that matches with this configuration, then at that case M chooses one of them, either this or that, which leads to non-determinism. Another, wherein the delta contains no transition that matches this configuration. At that case, the computation that leads to that configuration halts without accepting. So, what do you mean by accepting and rejecting? Let C be a computation of M on input W, which belongs to summation. Then this computation is called as accepting the configuration if and only if C is equals to starts with start symbol, initial state for the string W, stack empty. For multiple instances or multiple yields, it derives q epsilon epsilon, where q is it has reached the final state with input symbol consumed and stack symbol empty. It means what? A computation accepts only if it runs out of the input when it is in an accepting state and the stack is empty. Input is consumed, stack is empty. If it is in the final state, then the string is accepted. Then, when it is rejected, when C is equals to S W epsilon, which derives Q W dash alpha, where C is not an accepting computation and where M has no moves that can make from this configuration. Hence, a computation can reject only if the criteria for accepting has not been met and there are no further moves that can be taken. Coming to the language, if W is a string that is an element of summation star, then N is accepted, M accepts W when, if and only if at least one of its computations accept, and when M rejects W, if and only if all of its computations reject. And the language accepted by M, denoted by L of M, is a set of strings accepted by the machine M. M rejects a string W if and only if all paths reject it. It is possible that on input W does not belongs to L of M, M neither accepts nor rejects. In that case, there is no path that accepts and some path which does not reject. At that position, we say that W does not belong to that particular language. One more terminology, that is transition. What do you mean by transition? Now I say I have the current transition Q1 C gamma tends to Q2 gamma 2. It means what? I am at state Q1. If the input matched is C and the topmost element of the stack is gamma 1, then we move from state Q1 to Q2. Input matched is C2. So, what to do at that time? Pop gamma 1 and push gamma 2 into the stack. From Q1 to Q2, we can take C will remove from the input, gamma 1 will be popped from the stack and gamma 2 will be pushed into the stack. But what if C is equals to epsilon? C is equals to epsilon, it means what? without consuming the input, it will move from Q1 to Q2. Next, if gamma 1 is epsilon means what? Without checking the current status of the stack, whatever may be the content of the stack, okay, what we do? We go for moving from state Q1 to Q2 and push gamma 2 into the stack. Next, if gamma 2 is epsilon, it means nothing is being pushed into the stack. Move from state Q1 to Q2 for the input string C and pop gamma 1. No need to push gamma 2 because gamma 2 is epsilon. So, these are the three possibilities where if C is epsilon, then without consuming the input, perform the transition. If gamma 1 is epsilon, then without checking the status of the stack, perform the transition. If the stack is gamma 2 is epsilon, then no need to push onto the stack. So, with these terminologies, now quickly let us go through designing a simple PDA. Again, go back to the same language, PDA for balanced parenthesis. So, we have taken only one type of parenthesis, and then the definition of this PDA is M is K summation tau delta SA, where what is K? The number of states. So, here we will take first the simplest easiest PDA, wherein we have only one state, that is S. Summation is opening and closing parenthesis. Tau is only opening parenthesis. Final state is S. Coming to delta transitions. How you will design this language? What are the possible strings of this language? First you tell me. Yes, balanced parenthesis. What are the possible strings? First one is epsilon, right? So, initial state will be the final state and we have taken only one state PDA here. Then, what are the next possible? Opening parenthesis, a pair of parenthesis. Next, it can be sequence of parenthesis, opening and closing pair. Then, it may be nested parenthesis and so on. Now, for this language is not a regular language, but it is context free because already we have written context free grammar for this language in the previous sessions. Now, I have to design a PDA for this. So, how to design a PDA and accept a pair of balanced parentheses? What can be the logic for this? Your state is somewhat like this, okay, and if the input string is say opening parenthesis, a nested parenthesis and a sequential parenthesis, this is the input string. Whether this input string must be accepted by this language or no? Yes, it is accepted. We have derived it for the context free grammar. For the same string, I must be able to design the PDA. So, how you will design? You have a opening parenthesis must be paired with the closing parenthesis, and opening parenthesis must be paired with the closing parenthesis. So, what will be the logic applied? Whenever I come across a opening parenthesis, irrespective of what is there in the stack, so what I will do? I will push it into the stack. So, what will be the rule? I am at state S1, I come across a opening parenthesis and I do not check the top of the stack, irrespective of top of the stack. If I come across opening parenthesis, then be in the same state and push opening parenthesis into the stack. So, again I have one more opening parenthesis, so I will push it by applying this rule. So, these two are over. Next, I come across a closing parenthesis. So, how will do this? If I come across a closing parenthesis, then what I must do? I must pair this closing parenthesis with this opening parenthesis. I must count opening, closing. So, what to do? At that time, if I am at state yes, if I come across closing parenthesis and if my topmost element of the stack is opening parenthesis, then be at the same state and pop the topmost element of the stack. So for this opening parenthesis, this closing parenthesis been popped off. Next again I came across closing parenthesis. Again by rule 2 will go for popping the topmost element of the stack. Next I came across opening parenthesis. By applying rule 1, push opening parenthesis in the stack. Next when I come across closing parenthesis, at that time pop the topmost element of the stack. Input is consumed, stack is empty. If you have reached the final state, then the string is accepted. So these are the two rules written in this PDA, and the pushdown auto machine transition diagram looks like initial state. Since epsilon is the first string, initial state is the final state, and we have only two transitions here where S opening parenthesis, epsilon pushes opening parenthesis, and one more is S closing parenthesis, top of the stack is opening parenthesis, then pop the topmost element of the stack. So these are the two rules, and this is the pushdown automata, and this is the definition consisting of yes, two terminal symbols, and if you see here in the stack we are pushing only the opening parenthesis, the stack symbol is only opening parenthesis, and the final state is yes. So this is the transition diagram, and these are the two delta transitions obtained from this grammar. Now using these delta transitions, so this is the definition of PDA. Now I have to check whether the given string is accepted by this particular language or not. So we will take the same string. What is the initial configuration? Start state is yes, input string is opening parenthesis, closing, opening, and stack empty. This yields, this is the initial configuration, this yields what? Yes, opening parenthesis epsilon. By applying first rule, be in the same state, consume this, and what to do? Push opening parenthesis into the stack. Next, yes, opening parenthesis, irrespective of whatever is there in the stack. When I come across opening parenthesis, again what to do? Yes, consume this and push opening parenthesis into the stack. Now if you see here, yes, closing parenthesis, opening parenthesis. By rule 2, what to do? There is a match of one opening and closing parenthesis, so pop the topmost element or the opening parenthesis from the stack. So I'll get yes, pop, so I'll left this. Then again yes, closing parenthesis, opening parenthesis. By applying rule 2, yes, opening, closing, and pop, so I'll get epsilon. Yes, opening epsilon, rule 1, be at same state, consume that input, push on the top. And last, applying rule 2, yes, input is consumed, nothing is left over, and stack is empty. If you see here, will this string be accepted? Yes. Why? It has reached the final state, input string is empty, stack is empty, hence the string is accepted. Now, we will take one example wherein the string will be rejected. So, shall we take this string? Opening, opening, and closing. Yes, opening parenthesis. So, irrespective of what is there in the stack, what we will do? We will push it into the stack, and leftover is opening and closing. Next, yes tends to opening, irrespective of what is there in the stack, again push the opening parenthesis. Next, yes, closing parenthesis, opening parenthesis, what to do? Be in the same state, input is consumed, topmost element of the stack is popped, left with. Now tell me, we are in the final state, input is consumed, can this string be accepted? No. What is the condition? I must be in the final state, input string must be consumed, stack must be empty. Is the stack empty here? No. So hence this string is rejected because it doesn't have balanced parenthesis. So this case wherein stack was not empty, input is consumed. We will take another case wherein yes, opening parenthesis. So first we will push that opening parenthesis into the stack. Then yes, closing opening means pop the opening parenthesis from the stack. Now if you see here, it has reached the final state, stack is empty, but the input stream is not empty. Hence this string is not accepted, it is rejected. So I hope it's clear how to design a PDA and check whether the given string is accepted or rejected. So here is an example of what we discussed just now, an example of accepting the string. Final state, input is consumed, stack is empty, hence the string is accepted. One more example wherein it has reached the final state, but input is not yet empty, but stack is empty, at that time it is rejected. And one more case wherein it has reached the final state, input string is empty, but the stack is not empty. So this also the case wherein the string is rejected. So this is example for balanced parenthesis. Similarly for a raised to n, b raised to n, the same logic can be applied, but here we go for having two states, state S and state F. So a raised to n, b raised to n, where n is greater than or equal to 0 means the first string will be what? Epsilon. So initial state will be final state. So irrespective of what is there on top of the stack, whenever you come across all A's, push all A's into the stack. So and be in the same state, yes. Once you come across first B and the top of the stack is A, then what to do? Pop A and move from state S to state F, and this may be first B. Now for first A and B pair, for next number of A's and B's pair, if the topmost element is B, topmost element of the stack is A, then pop A and B in the same state S. So the delta transitions obtained are start state. If I come across A, irrespective of topmost element of the stack, push A into the stack. When you come across first B, topmost element is A, then move to state F and pop the topmost element A. Then in F, input symbol is B, stack symbol is A, then pop the topmost element and be in the state F, where F is the final state. So if you see here, S tends to the input string is AA, BB, S, A, epsilon. So A is pushed into the stack by rule 1. Next S, A, irrespective of the stack content, if you have A, push A into the stack. Now S, B, A, first B and topmost element is A, then change the state from S to F, B is consumed, and pop A from the stack. And in F, again I have a B as an input symbol and stack topmost element is A. Then again what to do? F, B, A, B in the same state F, consume B, pop the topmost element of A. And now you can see here, you have reached the final state, input is consumed, stack is empty, hence the string is accepted. So same way we have an example for rejected string wherein you have 2 A's and 3 B's. 2 A's pushed and 2 B's, when I come across 2 B's, these 2 A's are being popped, and at last I am left with one input symbol B, but stack is empty and we have reached the final state, but still this string is not accepted because the condition is it must reach the final state, input must be empty, stack must be empty. One more example of string PDA, WC W raised to R, wherein in state S we go for recording all the possible symbols of AB in W and push it into the stack. When I come across C, just do nothing, move from state S to F, such that in F you go for checking whether it is W raised to R. How do you check whether it is W raised to R? You can see here, when I have a push A into the stack, you have a B, then B, push B into the stack. So, these two rules will push W string into the stack. When you come across C at the stack, at the state S, when you come across C, irrespective of what is there on the stack, just move to the next state, that is F, to read W raised to R. Then matching W raised to R, which is nothing but a palindrome. So, at F, if input A and the stack topmost element both are same, A or B, then the topmost element must be popped. Just quickly we can see an example here. A, B is being pushed. When you come across C, just change the state from S to F. Now, F, B, A, topmost element input is B, topmost element of the stack is B, then it is been popped. I am left with F, A. Similarly, F, input is A, stack is A, both are same, then pop, and finally we have reached the final state. Input string is empty and stack symbol is empty, hence the string is accepted. So, these are some of the simplest languages. One more language, last one we will discuss here, A raised to n, B raised to n. What are the possible strings? For one A you will be having two B's. So, what to do at that time? So, for one A I will go for pushing two A's into the stack. So, for every one A I push two A's into the stack, means number of A's will now be equal to number of B's, and then the next rule will be as it is for A raised to n, B raised to n. So, these examples you can try out as